Go.
Hi everyone. Today we're presenting our motion planning final project, which is about multi-agent pathfinding, in short, MAPF. And I'm Siyuan, and I presenting along with Shiva and Dheeraj. And here is a summary of our project. And since I already talked about in the last presentation, we'll just glide over. So what is MAPF? So the problem formal definition, or description is below. Like initially there's a 2D square grid with n agents occupying n cells, and there are also some obstacles in the environment. And cells containing the agents and obstacle are blocked, and a different cell that is not an obstacle is assigned to the goal for that agent. And the problem is to move the agents from their current cells to their respective goal cells in discrete time steps. And we're trying to minimize the task completion time, which is also known as make span. And during each time step, each robot can wait in its current cell or move from its current cell to an unblocked neighboring cells, which is the four connecting cells around it. And the robots are not allowed to collide. And so why is MAPF important? Here are some application impacts that can potentially be beneficial from solving a MAPF problem. First, in robotics, we can coordinate multiple robots to work together in a warehouse or a manufacturing plant or even a hospital. And MAPF algorithm can help ensure that these robots move efficiently without colliding with each other, and thus reduce the risk of damaging to the robot and the environment. And also in gaming industry, we can use this to model multiplayer, or use this for multiplayer games, where like there's always multiple NPC characters navigating in a shared environment. And another environment that we might use MAPF algorithm is supply chain management, where MAPF algorithm can be used to optimize logistics and supply chain management. Yep.
I'll continue with the related work. So I'll glide through these slides quickly as we have already been through this before. So the first work is titled Multi-Agent Pathfinding Definitions, Variants, and Benchmarks. So this is a paper which proposes a unified terminology to describe and classify the MAPF problem and its variants. This paper also establishes a common benchmark and evaluation metrics for evaluating various algorithms. And it also has introduced a new MAPF benchmark suite, which consists of diverse set of maps, which has start and goal position for robots. And it also provides a standard MAPF algorithm as a baseline to compare different implementations of MAPF algorithms. So the one of the first method which we're going to be discussing is called config-based search, in short CBS. This is the state-of-the-art optimal planner for the classical MAPF problem. And this is a two-level planner. There is a high-level and a low-level planner. More of this will be discussed further in our implementation work and the results. So I'll be just quick with it. And the next algorithm is called as symmetry breaking constraints for grid-based multi-agent pathfinding. So there are certain drawbacks with the CBS implementation as the grid size increases, the number of nodes expanded by CBS increases exponentially. So this in, increases the compute time for CBS. So what this paper does is it builds on top of CBS. It adds symmetry breaking constraints to resolve symmetric collisions, so that it can eliminate permutations of pairs of conflicts easily, so thereby exponentially enhancing the compute time of CBS. And then there are a few other papers in relation with this project. So there's a paper called Multi-Agent Pathfinding for Large Agents. So the algorithms which we discussed before are solely for robots which occupy only one cell at a particular time. Those are called as point robots. But this paper describes methods for a different variant of MAPF called LMAPF, that is large agent MAPF, where a robot can occupy more than one cell at a particular time. And there is another paper called multi-agent pathfinding with mutex propagation. This paper presents a mutex-based symmetry breaking technique, which is far more effective than the actual symmetry breaking constraints. And it also proposes a mutex-based conflict selection strategy that enhances the existing CBS framework to significantly improve its success rate and runtime. So there is a state-of-the-art paper called as lifelong multi-agent pathfinding in large-scale warehouses. So this paper has introduced a novel framework called as rolling horizon collision resolution. So this algorithm is so powerful that it is capable of producing high-quality paths for up to 1,000 robots in real time, significantly outperforming any of the existing methods at present.
In our project, we're mainly focusing on implementing conflict-based search and symmetry breaking and mutex propagation algorithm. After we implemented these three algorithms, we'll simulate the agent's motion using Pygame, and we will make a custom Pygame simulator which acts as a ROS client, and each MAPF algorithm would be a ROS action server. And after that, we'll evaluate the performance of above algorithm with increasing number of agents on different benchmark maps. And the following are the work we did and the result we get. So first, we developed a custom Pygame environment to create a interactable simulator to configure custom maps and agents start and go configurations. Through the Pygame environment, user can easily change the size of the map, place or remove obstacles, and add or remove agent start and go pairs. Once the user has finished setting up the environment, they can simply press a key to run the underlying and MAPF algorithm chosen. Then the MAPF algorithm will return the path of each agent if a collision-free solution can be found. Given the path, the Pygame simulator will then animate the movement of each agent over each time step. Here in the simulator, the white cells represent empty grids, and black cells represent obstacles. Colored cells with numbers indicates agents, and colored cell with italic numbers indicates the agent's goal. So in order to add scalability, fault tolerance, and flexibility to our system, we split the Pygame interface and each MAPF algorithms into their own ROS nodes. We designed a combination protocol with ROS action client and server architecture. Now the Pygame interface have clients that can send requests for planning of the selected algorithm. And once the MAPF server receives a request, it will start planning for a path and send result back to Pygame for animating once the planning finishes. Once the server, while the server is planning, it also sends back feedback information such as like number of nodes being constructed. So after we have integrated ROS into the system, we'll also integrate our system into a containerized environment with Docker. And each individual components are now launched in their own containers. This potentially allow us to take advantages of distributed cloud computing to test bigger maps with more computation capability. With the integration of containers, it's also made possible to instantly restart an algorithm server if it dies unexpectedly.
So the first algorithm which we have implemented is the CBS algorithm, which is the conflict-based search. So conflict-based search algorithm consists of two aspects. So the first one is high-level CBS, and the second one is the low-level CBS. Next slide, please. So The following tree is used by the high-level CBS. The tree is also called as the constraint tree. So what it does is nothing but, let's say in this particular example, we want the robots or the rats to move from point one to its goal, which is the cheese one, and rat two to move to its goal, which is cheese two. So we form a set of paths. Basically, initially, what our algorithm does is high level conflict based search. It just takes in each agent and it gives it to the low level conflict based search algorithm in order to find individual paths of each robot or the rats in this case. So once we get the individual paths of the robots, what we do is we try to find the conflicts. Conflict is nothing but whatever you can see is highlighted in red. So the conflict here is found at time step 3, which is at B2. So once this is done, so there are two kinds of conflicts again, which is the vertex conflict and the edge conflict. So vertex conflict is nothing but when two agents try to enter the same vertex at a particular time t. But edge conflict is nothing but, let's say, two agents are trying to interchange their positions. That is called as the edge conflicts. So these conflicts will be resolved separately. So in the left node of the child, what it does is, what our constraint tree does is, it imposes the constraint on the agent one, that it says agent one to not be at that particular node, which gives rise to a conflict. And then in the right tree of the in the right node of the constraint tree, it says agent 2 to not be in that particular node at that particular time instant. It kind of iteratively solves this until a solution is found. So that's the entire algorithm of the conflict based search. Next slide, please. So this is the high level CBS which I described. So high level CBS uses constraint tree and gives individual path finding tasks to the low level CBS, which uses next slide, please. Low level CBS uses simple A star algorithm in order to solve resolve the conflicts which arise at each level of the constraint tree. Next slide, please. So these are the results of the conflict-based search, which we got in our using our Pygame interface. You can clearly see that there are multiple agents and there are obstacles in the environment, and the conflict resolution is being done pretty well, and they are able to find the agents are able to find their respective paths properly using the conflict-based search algorithm. Next slide, please. So Dheeraj will continue from here.
So moving on with CBS, there are few drawbacks and limitations to the conflict-based search. So first and foremost is that as the search space dimension increases or the grid size increases, the number of nodes expanded by CBS to resolve the conflicts increases exponentially. As explained by Shiva, the high-level CBS expands each node present in the conflict tree in order to solve the conflicts and find a solution to the MAPF problem. So in this case, we can consider this example test case, which is shown on the right in the image. There are 4 agents in an 8 by 8 grid, wherein each agent starts at the corner of the grid and goes to the whose goals are at the other side of the grid. And we can see that each agent's optimal path conflicts with every other agent's optimal path in this case. So what happens here is that the CBS has to resolve all these conflicts occurring between the multiple permutations of the pair of agents and their conflicts. So what happens here is that in this case, the CBS failed to find a solution. So when we ran the CBS program on this test case, so it ran indefinitely and it was unable to find a solution. We added a termination condition such that the maximum number of nodes expanded would be around 100,000. So even after adding a threshold, the CBS was unable to find a solution. So the table here represents the number of nodes expanded by CBS on a MAPF instance for a pair of agents. So you can see for the given above 8x8 grid, it is somewhere around 573,000. And since we have 4 agents and there would be like four or more combinations of agents which would be in conflict. So it will be around 2 million nodes that need to be expanded, which is highly unfeasible. So in order to solve this problem, uh, symmetry breaking constraints come in. So what are these symmetry breaking constraints? So as we saw that as the grid size increases, CBS greedily solves each and every node in the constraint tree. So what symmetry breaking constraint does is that it adds few symmetry constraints called as barrier constraints whenever a symmetry is detected in a map. So for example, if you see on the image on the right, SI and GI are the start and goals for the for the agent I, and SJ and GJ are the start and goal positions for the agent J. So in this situation, we can see that whenever the low-level CBS finds an optimal path for both the agents, there is always a conflict within this yellow highlighted rectangle. And so the authors in the symmetry breaking research paper have proved that there will be, whenever the CBS adds a conflict and resolves it, it has to resolve each and every conflict present inside this rectangle. So CBS expands 6 nodes in order to solve this example problem here. So what symmetry breaking constraints do, that they add a kind of barrier constraints for each agent so as to solve these conflicts in one go. So there is a new algorithm called a CBSHCR, which stands for conflict-based search heuristic cardinal rectangle reasoning, which enhances the CBS performance exponentially. So we'll discuss few results of the CBSH versus CBS. So you can see the example problem which I described earlier. So this is the result for that. You can see, as I said, CBS expanded 6 nodes, whereas CBSH with symmetry breaking expanded only 2 nodes. And we can also see for this test case, wherein we have the same example of 2 agents, but with a larger grid, with an 8 by 8 grid. And here you can see that CBS has expanded 126 nodes to find a optimal path, but whereas CBSH has expanded only 2 nodes. So we can see that CBSH CR is way more faster and efficient than CBS. And we have another test case wherein there are 4 agents. This is the case which I earlier explained, where CBS fails to find an optimal path. So CBS has expanded more than 100,000 nodes, and still it was unable to find an optimal path for this example test case. But whereas CBSHCR with symmetry breaking constraints was able to find an optimal solution for all the 4 agents in just 2,152 nodes. So we can, from these results, it has been proved that CBSH CR with symmetry breaking is far more efficient and faster than the normal conflict-based search. However, even CBS with symmetry breaking is not a more generalized algorithm. So there is a peculiar test case where even CBSH CR also fails. So this is a test case where there are 4 agents, but with obstacles at the corner, at each corner. So in this case, both CBS and CBSHCR fail to find an optimal path within the 100,000 node expansion threshold.
So mutex propagation is a more advanced algorithm which aims to resolve the mutual, which is nothing but it is short for mutual exclusion. It is used to identify the possible joint states of 2 agents exactly and resolve the cardinal conflicts. Cardinal conflict is nothing but when all the it 2 agents are said to be in a cardinal conflict when all the shortest paths of the 2 agents collide. So you can see that in the particular examples which we have, cardinal conflicts occur in the highlighted areas in examples A and B, and in example C and D also there are cardinal conflicts occurring. Next slide, please. So we use the concept of multi-value decision diagram, so which is nothing but a leveled directed acyclic graph that consists of all the shortest paths of the agents. So let's say we have agent 1 and agent 2. So we construct a multi-value decision diagram for each agent which is nothing but a breadth first search is performed, and at each level the nodes are identified, and all the nodes that are included in the that come in finding the shortest path from an agent start location to the end location are included in the multi-valued decision diagram of a particular agent. Oh, yeah. So, coming to the concept of mutexes. So, what we do is we find two agents. We find the agents which are mutex at a particular level, which means nothing but two MDD nodes are mutex if and only if all paths from the first agent to L1 I mean, L1 is a particular node, and from the second agent to L2 is a particular node in MDD2. So if both of them collide at time t, they are said to be mutex. So let's say if you consider level one, you can see that we highlight several initial mutexes in the left hand side of the image, which are highlighted in blue, which means you can see that in level one C2 is present in MDD1 as well as C2 is present in MDD2. So they both are initial mutex. So like this, we form the initial mutexes of the entire MDDs of both the agents. And then we come to the mutex propagation. Mutexes are said to be propagated if all the parent nodes are either initial mutex or propagated mutex. In this manner, we propagate the mutex starting from level 1 to level 5, and then we check at level 5 whether goal nodes are in cardinal conflict. Next slide, please. So if the goal nodes are in cardinal conflict, we introduce certain constraints um, in order to resolve those mutexes, in order to resolve the cardinal conflict. And so this is the mutex propagation algorithm that is used in order to resolve that particular cardinal conflict which arises. So once we determine the cardinal conflict, we determine the constraints. So for constraints for each MDD starting from the pre-final level, we pick a node from the MDD. Let's say we pick the node B4 in level 4. So what we do is we check whether it is mutex with all the other nodes, the other MDD at the same level. And if it is mutex with all the nodes of the other multi-value decision diagram. So let's say we take the blue B4. If it is mutex with orange B4 and orange A3, then that is nothing but a constraint which we'll be introducing. We will say that agent 1 cannot be in location B4 at uh, time step 4, which is the level which is corresponding to the level of that particular multi-value decision diagram of that particular agent. So that's how we introduce constraints and we resolve them all at once. So next slide, please. But I mean, we have tried to implement mutex propagation algorithm in our work, but uh, we are getting a set of paths, but we are currently having conflict in those particular paths which have been found. So we need to debug the algorithm in order to obtain the desired result. So these are the current results which we have obtained through mutex propagation. Next slide, please. So coming to the experiments and evaluation part. So we will be testing our algorithms on publicly available different benchmark maps and data. So from the MAPF website. So each map is of varying size and complexity. And our evaluation metric is for each map, the success rate can be calculated for the algorithms and compared against the number of agents solved for a particular map. Next slide, please. So this is our team, and this is how we have distributed our work. And thank you.